Today we're exciting to share this topic or the project that we've been working together for quite some time, assessing urban form and climate justice with using deep learning technologies. And once again, it's very honored to be invited to the Thai series. And yeah, just great to be here. So for today's talk, I will start with some overall introduction, and then Yuzhou will be able to dive into the details on the technology side of our project's innovation. And why is it important to study this is because that I think we can all agree that the climate change is continuing to progress, and that urban pattern of urban or cities are really a deciding factor where the devastating effects, air pollution, heat islands, and all sort of climate injustice will happen differently in urban region. And these impacts are quite different to its urban residents, and because urban form kind of infers underlying structural racism through the landscape, the structures, and the infrastructure disparities that within the urban region. And then how does it develop throughout time? So the historical pattern, the present day pattern, and the future pattern is quite important in understanding this change and how it impacts different residents of the region. And in the US, we have study again and again shows that minority and marginalized communities, they do experience greater exposure to either ambient or point source air pollution and overall higher urban temperature that during their daily life. So that leads to hazardous impact on their health, and that includes respiratory infections, disease, and also long-term health condition, such as chronic health conditions. So it's quite important issue to be studied. Next slide, please. This is one of the example that we can look at the relationship between urban form and how we have been studying it so far. If we look at the map on the lower left, the top row is Los Angeles, and you can see that breaking the air quality is in the background as a gray scale from lower PM 2.5 to higher, darker black concentration of PM 2.5 air pollutions. And on top of that is four grades of the redlining in the historical from the historical data. And you can see the grade D, which is the highest grade of identified as the most vulnerable or most redlined area, actually has overlap with the highest concentration of PM at the nowadays. So there's a historical effect that goes into the nowadays concentration. If we combine that with the overlap on the right side, which is the isolation index, is one of the social determinant of health, STOH, as we use, you can see that some of them are overlap. And these STOH index are the well-used index to study disparity, climate injustice, but you can see that either in LA or San Diego, in San Diego, we look at temperature. Also, left side is redlining, right side is the isolation index. But for Hispanic and Latinos population, there are overlaps, but also there are also not being recognized area, which also experience high temperature or high concentration of PM. So we need to increase clarity between these relationships and a better way to assess how do we make changes or support decision making to make change in the long run. Next slide, please. So underneath, if we take a step back, there's a systematic bias that creates the need for studying the differences here. So on the left side, we have the contextual social determinant of health, SDOH. This can represent exposure, such as to air pollution or exposure to road network noise, and access, which is a positive side of exposure, access to park, green space, and all sort of resource to be used. And also social demographic, such as the residential isolation that we use in the previous slides to understand differences. But however, these measures, although they are well studied, they have bias and limits. For example, a lot of times these measures or indexes are calculated every 5 years, 3 years, even longer. So it doesn't really capture the frequent update or changes in terms of urban space and population changes over time. And also some of the data are collected through surveys, and the design of any survey will always have some sort of bias or heavily lean towards a population against other population. So there are bias and limits in all the existing social determinant health measures. That's why we want to utilize deep learning on a separate way, but not replacing SDOH. Instead, we want to use what we can capture from deep learning, the urban forms and latent features, and use it in tandem with traditional SDOH measures. Next slide. So if we put that in action, we have a satellite imagery cross deep learning approach. And satellite imagery has become very easily accessible. A lot of imagery are public available. The quality of the image, the resolution of the image, and the spatial and temporal coverage of the image has been growing over time. And so it's very easy accessible to all the researchers. And we want to take that and utilize this as our advantage and select different type of deep learning models, try to extract urban forms in different ways. And then with that, we can have actions to better assess the environmental risk prediction, the impact on urban form to outcomes, and then put that back into action and changes into the community collaboration. Next slides. So the data set we'll be using, we'll talk about today, is two satellite imagery using Landsat and Sentinel. These are two public available imagery data sets. Landsat is the lower resolution, is 30 meter resolution each pixel. And Sentinel is higher resolution, 10 meter resolution. So on the left side, you can see that although they're looking at the same area, there are differences in resolution. And that's also very interesting to us because we want to test how the models and algorithm can get information out of different type of resolution imagery. Next step. So once we take the image, we tiled it into smaller area coverages, small tiles. Each of them cover 450 meters. So for Landsat, it's 15 by 15 pixels. And Sentinel is 45 by 45, just because of the resolution itself. And one of the limitation here is we use the center or centroid of the image to coordinate that to represent what the end feature will represent on the map. Next slides. Yeah, take away, Yuzhou.
Okay. Yeah, thanks, Jay, for the nice introduction. So next, I will introduce the methodologies and the performance of our project. So first is to analyze the previously mentioned either the low resolution or the high resolution set of images. So in here, when we consider using the first model we consider using here is the convolutional neural networks. So as we know, in the recent years, the convolutional neural networks actually achieved very promising the performance, especially for the image learning tasks, for example, like the image classification, the image segmentation, and so on. And the ResNet, so which was proposed by the Community in the year 2016, actually is one of the most representative of the convolutional neural networks. So which actually introduced skip connections mechanisms. So in this case, by using these skip connections, it can solve the vanishing or the exploding gradient problems in the very deep convolutional neural networks. So in this case, people can build a very deep, for example, 1,000 or 10,000 neural networks by adding this skip connection mechanisms. And in our study to study and to deal with the lower and the high resolution set images, here we consider using pre-trained ResNet 152 models. So here the 152 represents for the ResNet we consider using. So here contains the 152 layers, and the pre-trained means actually the weight of this ResNet 152 model actually is generated based on the pre-training on the ImageNet dataset. Okay, and then so that is the bottom line is we utilize the pre-trained the ResNet model and here as a baseline. Okay, and to analysis the given the lower or the higher resolution satellite images, and then we will compare with the other geometric deep learning models. And the figure 3 here gives the overall architecture of the pre-trained ResNet 152, and you can see that. So for the input image, we have the 3 channels RGB, right? And here the resolution size is 224 by 224, and then after the several the convolution blocks, so you can see for each convolution blocks contains the convolution operation and the maximum or average pooling, and then is the convolution and operation, convolutional operation. Okay, so after this, the 6 convolutional operation, the blocks, and then we applied the average pooling, and finally we feed it into the MLP to get the final output from the pre-trained ResNet 152 model. And here, since in our study, given based on the given the set images, we actually we don't have the ground truth, and also we don't have any descriptions or the nodes which can give more more external information about the given images. So in this case, we will conduct the unsupervised learning. So that is, we don't have the exact number of the classes. Okay, so in this case, what we did is we will use the pre-trained ResNet 115 model, so and apply it to the given images, and then we can get a embedding. And here we don't use the embedding from the last layer. Actually, we extract the output embedding from the final layer prior to the fully connected layer. So in this case, we just use the one intermediate the output from the pre-trained ResNet 152 model, and then we feed the intermediate embedding to the unsupervised learning model, for example, like the KNN. Okay, and then we can assign the predefined number of the clusters to the KNN, so which can give us the final clustering results for the given images. Okay. And the figure 4 here shows a toy example. So suppose we have the input satellite images, okay, and through the different layers, okay, within this pre-trained ResNet 152 model, so you can see actually the output embedding from different layers. Actually, they are very different. Okay. But however, to apply the convolutional networks to the satellite images, especially for the high resolution images, there are some the challenges and also some drawbacks. So the first thing is, as we know, to feed the images to the CNN-based model, we always need to make sure all the images they share or they have the same image format and the size, right? So otherwise, we need to do either the up or the down sampling. And second, especially for the high resolution the satellite image, we may need to require the enough the memory and the computational cost for that. Okay, so that is it is a high computational cost. And the third one is by using the CNN-based model to study the pixel-wise information, somehow we always may miss thing to capture some the local structural information. Okay, so to deal with this challenge, here we consider saying to convert the input satellite image to the graph representation. And the methodology here we consider use is the simple linear iterative clustering SLIC. Okay, and the idea behind that is actually is very simple. So that is given image. Okay, so we do the segmentation, and then we can generate the super pixels Okay, so which is based on the segmentation results. So that is, and the segmentation here we can consider using either the iterative clustering, or we can use the k-nearest neighbors, this unsupervised learning method. Okay, and the benefit of using the shoe pixels instead of the pixel information, and the as follows. So the first is computational efficiency. Since, as we know, the shoe pixels actually can provide the compact and the convenient representation, okay, of the original image. Okay, and the second is the noise reduction. Since, as we know, by grouping each pixels or the pixels into shoe pixels, so the some minor variance and some noise can be averaged out. So in this case, by focusing on the shoe pixels, we can derive some more robust feature for the given image. And the third one is compare with the pixel-wise information. So shoe pixel can maintain the spatial coherence and also can capture the local structure better than the pixel-wise information. Okay, and so the figure here gives the very the illustration of how we can convert the input image to the shoe pixel graph. Okay, so first from A to B we do the segmentation, so we can determine which part can be the shoe pixel, and after that we just do the concatenation, okay, between any adjacent shoe pixels. Okay, and for the implementation, actually it is very simple. So that is, we have the target image denoted by the eye, and then we predefine the number of the shoe pixels. So and then we can feed this information into the SLIC algorithms, and then we can generate the shoe pixel matrix. Okay, and algorithm 1 here gives the more details about how we can generate the regional adjoint graph RAG. Okay, so that is we can also treat it as the shoe pixel graph. Okay, and yeah, here I also would like to highlight one more time about why we consider using the shoe pixels instead of the pixel-wise information. So, for example, you can see in this figure, the left side is saying to apply the traditional convolutional operation, okay, on the pixel-wise information. Okay, so here you can see there is a box, right? And suppose the middle box here, middle cell is a target cell, is a target the pixel. So you can see by conducting the convolutional operation over this pixel, we can only allow to exchange the information, okay, between this target pixel and its one home neighbor pixels, right? So we can only conduct the small scale, the regular region, okay? But you can see on the subfigure B here. So once we convert this the image to the shoe pixel graph, okay, then we can conduct the convolution operation on the large scale irregular region, okay? And here you can see, suppose the red point here is a target shoe pixel, okay? And then we can also derive the similarity or the weight, the weight of the connectivity between the target shoe pixel and the adjacent shoe pixels. Okay, so in this case, compare with the regular shoe pixel information. So by modeling on the shoe pixels, we can better capture some local and some more global structural information. Okay, and figure 5 here shows we are using the low resolution satellite images as the input, and then we conduct the segmentation and generate the corresponding the shoe pixel graphs. And the figure 5 shows the different shoe pixel graphs with the different number of the predefined shoe pixels. Okay, and the figure 6 here shows the flow chart of how to generate the final shoe pixel graph from the given set of images. right? So from A to B, we do the segmentation, and then from the B to C is for each segment, we can treat as a superpixel, right? And then we do the connectivity. We add the connectivity between the connections between different superpixels, and finally we can derive the superpixel graph. Okay, so which can well represent the given original the satellite image. Okay, so by using the SLIC algorithms, so we can easily generate the superpixel graph from the given either the lower or the high resolution satellite images, and to model on over this the superpixel graph. So here we consider using the graph neural networks, and as you may aware, so in the recent years, the graph neural networks actually achieved the promising performance for the graph learning tasks. For example, like the node calculation, graph calculation, link prediction, communication, and so on. And moreover, actually the GNs can be applied to the different domains, not only limited to the network analysis. So that is the graph neural networks also achieved the very promising performance on the other domains. For example, like the image recognition and natural language processing and so on. And for the graph neural networks, actually it contains the three key components, three key functions. So the first is the message passing function, so which will determine what neural message needed to be propagated from the one hop neighbor or multi-hop neighbor to the target node. Okay, so for instance, in this subfigure, suppose the node A is the target node. So then we can conduct the message passing function over A, and the message. Then we can do the message exchange between A and its one hop neighbors. Okay, so that is node B and node D. Okay, and the second function is the aggregation function. So that is we can aggregate all the messages received by the A. Okay, and the third one is the updating function, so which can generate the new embedding for the target node A, so which is based on both its own the embedding and also the embedding learned from the one hop or the multi-hop neighbors. Okay, so this is the basic idea behind the graph neural networks. And so since, as we mentioned before, in this project, we conducted the unsupervised learning. And as we know, in the recent years, so the self-supervised learning, unsupervised learning actually is a very hot topic. And the one main approach for the unsupervised learning, representation learning, is the contracted learning. And here I will give a the brief introduction about the contracted learning. Okay, so for instance, so here you can see this subfigure, which is the screenshot is from the SimCLR paper, which is accepted by the SML 2020. Okay, and the idea is very simple. So suppose we have the input graph, input image X. Okay, and then for this input image, we can do the perturbation, we can do augmentation. So we can generate the two versions, xi tilde and xj tilde. So for example, to generate the xi tilde, so we just say to add some noise to the original image, and to generate the xj tilde, for example, we can resize or we can clip the original image. Okay, and after that, we will feed the xi tilde and the xj tilde to the student-based model, for example, to ResNet model. Okay, and then we can generate their corresponding the latent representation, HI and HJ. Okay, and after that, we will use two projections. So here you can treat the projection as the MLP. Okay, so which will map the representation to the space. Okay, so which is the contract loss is applied. Okay, so in this case, we can generate the Zi and Zj from the Hi and the Hj separately, right? And finally, we will conduct based on this Zj and Zi and Zj, where we will we will build our final objective loss function. Okay, so that is to maximize the mutual information content from these two representation. Okay, so this is a basic pipeline about the controlled learning over images. But for the network, we can do the similar way, right? Suppose we have an input network, and we can generate two views of the graphs based on this original input network. And the T1, T2 here represent two different the augmentation approaches. So for example, T1 can be saying adding nodes, and T2 can be saying removing edges. Okay, so in this case, we can generate two the augmented graphs. Okay, and after that, we will feed these two augmented graphs to the two graph neural networks, so denoted by the F, and then we can generate the corresponding node representation. Okay, and also we can generate the graph representation. So that is, we can think to apply the pooling layer over the node representation. Okay, and so after that, we can conduct the concept learning, right? And in the graph, we allow the three patterns. So the first pattern is we can compare the local representation. Okay, so that between the node representation, and the second one we can compare the graph concept learning. So that is, we can compare the graph level representation S1 and S2. And the third one is we can compare the node representation with the graph representation. Okay, so let's compare with the UI and S2 and the VI and the S1. Okay, so this is a basic the introduction about the concept learning over the images and the graphs. So also the graph networks actually achieve the very the stability, the performance on different tasks. However, the GNs can not necessarily capture some certain topological structures. So especially in the graphs. So for example, like the holes, the circles, tunnels, and so on. So some higher order structures or some local topological representation. But however, all these high order structures are actually very important and high relevant for the applications, so that require the connectivity information. For example, when we when we apply the GN graph networks on the molecules, so we can always find out that some high order structures. Okay, for example, here the triangles. Okay, this high order information also always plays a very important role for us to for the graph classification tasks. Okay. And so here is one more example to say the important to consider the high order information. So suppose we have the two networks, okay, left and right, and our target is these two purple nodes, okay, and based on just the geometric information, the two purple nodes on the left and on the right, actually they have the same node degree, right? So both of them, they have the three neighbors, but however, the two purple nodes, okay, on the right side, actually they are involved in the triangles. Okay, so in this case, from the topology perspective, they are different. Okay, but however, for the graph neural networks, always they will omit this kind of information. Okay, so in this case, to address these fundamental challenges, so here we consider instead of using the graph neural networks, we consider using the simplicial neural networks. So that is, we conduct the convolution operation not only on the nodes level, but also we apply it to the different dimensions of the signal complexes. Okay, so for instance, in the graph, the zero simplex is a node, two simplex is an edge, one simplex is an edge, and two simplex is a triangle, and three simplex is a tetrahedron. Okay, so that is, the simplicial neural networks always allow us to model over the different dimensions of the held information. Okay, and another example to show difference between the graph neural networks and the simplicial neural networks is, so suppose we have this the input graph, okay, and this black node is our target node. So by using the graph networks, we can always think to model this, to update the information over the black node. The information is from its one whole neighbors. Okay, so that is the information from the adjacent 4 nodes. But if we consider using the simple complex information, okay, so we can find out actually the features received by the target black node actually is from not only the neighbors, okay, node neighbors, but also from the connected the edges, right? And for the edge, the feature of the edge will receive information not only from the node or from the edge, you will also receive information from the involved triangles. Okay, so this is the rationale behind why we consider using the single complex neural networks instead of the graph networks. And inspired by these simple neural networks, and also based on the goal of our project, so we proposed Pixel, the simple convolution contractive learning S2CL model. Okay, so that is we integrate this high order structures, from the zero-dimensional to the two-dimensional, so and this information into the contractive learning framework. So that is we make the whole pipeline as the higher order structure well. And so here we will briefly introduce the general pipeline of our proposed Pixel simple contractive learning framework. So that is we will utilize the previous mentioned the SLIC algorithm to generate a pixel graph based on the given the input of the satellite image. Okay, and then we will conduct the simple graph convolution operation. Okay, on the pixel graph. Okay, so then we can generate the corresponding the simple complex based embedding. Okay, and meanwhile we will use the global pooling layer. Okay, and apply this pooling layer over the simple complex level embedding to obtain the graph level embedding. Okay, so here is we can generate the graph level embedding. Okay, and after that we will feed both the simple complex based embedding and the graph level embedding to the MLP. Okay, so that is we can generate the representation can be used for the contractive learning costs. And then finally is here we consider using the mutual. We use our objective is to maximize the mutual information. Okay, between the graph level representation and the simple complex level representation. Okay, so as we propose a new the contractive the loss calculation pattern. Okay, for the graph representation learning. And after that, we will feed the pre-trained embedding to the, for example, k-means, and we can conduct the final unsupervised the clustering. And the figure 8 here shows the visualization, the performance from the 3 models we used in this project. So the left side is the clustering results from the pre-trained REST network 132, and the middle shows the results from the infograph. So that is combining. So regarding this infograph, is they combining the graph networks with the contractive learning approach. Okay, and the right side is our proposed S2CL model. Okay. And here we display the external results based on our proposed S2CL model and compare with the ResNet 152 and the infograph. And the evaluation metrics we used here is we consider using the 3 evaluation metrics, including the silhouette score, okay, constantly the Harabas index and the Davis Bowden score. Okay, so for the silhouette score and the Davis Bowden score, so that is the for the Supervised score and the Kalinski's index. So the higher the better, and for the Davis Boolean score, the lower the better. Okay, and also for the number of clusters, here we consider the 4 different clusters from the 10 to the 40. Okay, and data sets we consider both the higher and the lower resolution satellite images. Okay, and from the table we can see that in general, our proposed S2CL model can always achieve the state-of-the-art performance compared with these 2 baselines, okay, across all the 3 valuation metrics, okay, and you can see actually the difference between our proposed especially the difference between our proposed S2CL model and the ResNet the 115 model is very large, okay, and there are some subcase that the infograph achieved the better performance than our proposed S2CL model, and actually is fine, since the first thing is the difference is very tiny and we may need to do more the tuning stuffs, and the second one is maybe it's due to the number of the instance in our data set. So in the further study we may also to apply our proposed model on the more large scale satellite image data set. Okay, so next Jay will introduce will give more information about the conclusion and some future work.
So based on what we're seeing in the experiment, first of all, the S2CO is, to our knowledge, the first work that employs the simplistical complex representation learning framework and GCN on supervised satellite imagery learning. Although satellite imagery has been utilized in deep learning for extracting different type of feature, but this approach remains to be the first in our experiment. And we evaluate our methods using real-world satellite imagery, lower resolution, high resolution, and yeah, as we just see in the table, it's outperformed the baseline or the well-used ResNet model and the pre-trained weights. And our next step, because the end goal or one of the major goals is to see what type of latent features and urban form we can extract using our algorithm to study the disparity and environmental impacts on different parts of the urban. So we want to evaluate using external measurements that includes the SDOH, so we can see whether it's representing similar aspect of the urban environment or it's telling us something that can use in tandem together to predict or to understand our urban region and outcomes. And also based on our proposed S2CO, we want to apply the framework to over the temporal scale, to multi-year, to utilize, because the satellite imagery are very, for example, Landsat, the satellite will go back to the same place every 14 days. So the data is very rich in terms of temporal coverage. You can capture small changes over time and also large development in urban area. And oftentimes these large development over time, a new construction area or a new zoning changes in urban planning and design will have huge impact on the residents and their exposure and eventually the long-term health outcome. So I think utilizing the imagery over time to find small changes and large changes are important to our goal. And that's why we want to see if we introduce this temporal feature, how does that change our ability to capture different type of latent features and to study the outcome. In this case, will be air pollution and heat island change over time. And we want to extend the temporal and spatial of our algorithm. Right now we have the experience on San Diego. We want to expand to LA, metropolitan area, and also Bay Area, which are the major populated area in California. And in the proposal, original proposal, we want to study until 2019. But yeah, everything changed or uh, significantly changed after COVID. So we want to extend that um, to study in between COVID and after COVID, whether the pattern changed or not. Next slide. And again, thank you for the time today, and supported by partially supported by this NASA grant and our great team of members that work together.
Thank you for the great talk, Jay and Yuzhou. And I would invite everybody to unmute and give a round of applause to our speakers. Thank you. Thank you again. So if the audience has any questions, please feel to unmute yourselves and ask. Otherwise, I can begin. So I wanted to ask, have you, so in this idea of simplicial networks, can you also include different topological features and persistence homology?
Yeah, certainly. Yes, that's very good question. Yeah, we can certainly involve the other topological summaries into and integrate it into our framework. Yeah, so maybe you can have the two channels. So one channel, let me go to the probably here. Okay, so one channel is, for example, is the stimuli complex representation learning, and one channel is about this, as you mentioned, some topological summaries representation learning, and then we can combine them. Yeah.
Okay. So I was wondering, this is just for COVID, but how applicable is it in other disease modeling areas? And is there also, besides disease modeling, is there any transferability to other sort of applications?
Yeah, absolutely. I think the main takeaway of the entire framework is really to understand the urban city patterns and whether what does that the patterns or the feature tells us, how does it represent the residents or the region's complexity, we have yet to know. So I think it can apply to, you can think of it, use it as a new metric to or index to understand. You can take it to study disparity, health outcome, concentration of certain disease. It could also contribute to that if the target of interest is related to urban formation. Of course, you don't want to take the features and study something entirely unrelated to urban forms. So as long as the target interest is related to urban formation or the connectivity of urban, which is why S2CO will thrive in this regard. As long as the understanding is trying to decompose the urban format and its connectivity to nearby regions, then we can utilize that.
Also, so I wanted to ask, there's this now, recently there has been this push for foundation modeling and a lot of, using very, very, very huge data sets to model precise, I mean, I wouldn't say, I don't know precise or not, but modeling, I guess, the underlying framework for a lot of these mechanisms. So where do you see your model having an advantage over these large foundation models?
Yeah, that's a very interesting question to that. So I'm not sure the foundation model you mentioned is the large language model, or you mentioned some models which is trained by a very large scale data set. So I think, no matter for the large language model or for some pipelines trained by the very large scale data set, I think one of the main advantage of our superficial simple complex learning, so that is the pipeline is very flexible and very efficient. Since as you know, if you want to, since we know the foundation, the model is very powerful, but however, to fine tune them, it also will be cost. Take some efforts and some cost, right? But for our model, actually, from the thing to convert the satellite images to the superficial graph, and the modeling on superficial graph based on the single complex information actually is very efficient. Okay, and also as you mentioned, so different from this foundation model, we can easily integrate any some topological summaries, okay, and also some other like the graph structure, local or global information into our pipeline. Okay, so our pipeline actually is very flexible here.
Okay,